So now I would like to switch gears a little bit. Is it okay to kind of move? So just want to some water. So doing demonstrations in front of a live audience is a bit difficult, especially when it's not your home ground. So things sometimes work and sometimes they don't. So I apologize in advance if things get a bit erratic. So at some point, I would request the organizers to turn off the lights at some point, and I would like you to be in close contact with me, right? So here in front of you is this is my sources of, this kind of board are my sources of light here, okay? And here I'm going to put in different kinds of objects and see the properties of those sources. Very simple. Okay, so the first source I have is this tube here is a laser. It's a 633 nanometers laser. It's called a helium neon laser, gas laser, produces red light. So the first thing I would like to show and try to show, and I apologize if it doesn't work because it requires time and patience. What I'm going to show is the interference. Simple interference. That when this light is acting like a wave. Now the point is that these are not quantum experiments. These are still with classical light, coherent light. But the title of my demonstrative session is A Peep into the Quantum World. Exactly the same ideas carry over if I were to use quantum light, if I were to use single photons. But it's refreshing in itself to see interference, okay? And these might look simple experiments, but I did a PhD in physics from Oxford University, and I've never seen interference in my life. Or if interference existed in nature, I just bypassed it with an air of nonchalantness. So when I first saw interference, I was kind of amazed. So I'm going to turn on the laser, and in the path of this laser, I'll put in a slit. A slit is a narrow kind of opening for the laser, and when light passes through this slit, its wave properties manifest, and the light just spreads out. And this light spreads out in a strange fashion. There are certain regions on that screen, that white screen that my friend at the Ghana University has built for me. There are certain regions on that screen where light never reaches. And there are regions where the light always does reach with a higher intensity. So automatically there is this spatial preference. Space is isotropic. It's the same everywhere. But all of a sudden, the wave nature comes to the fore and makes certain regions of space special. Light reaches those regions, and other regions, the light is unable to reach. So let's see if I'm able to make this work. I need a volunteer for this. Can I have a student come over and help me with the connections, please? Anyone, any volunteer? Come on. I'm not going to ask you questions. Come on, please. This is the whole point of it. Come on, please. Don't be shy, come on. What's your name?
It's Joseph.
Joseph?
Yes.
Joseph, all right. So we have Joseph here. So this is our laser. You wanna? I wonder, can you kindly, before I switch on the laser, so can you kind of put in these wires into this laser box? Red into red, green into green. Got it? So this laser needs power. Every laser needs to be powered up. It needs optical pumping so that the laser works. Now, the laser is a quantum device, by the way. Okay? I'll call you later. I'll call you later. You can sit, I'll call you later. All right, so now what I would like you to do, is it possible to turn off the lights a little bit? Audiovisual guys? Thank you. So, can you plug in the laser box? Yeah, this is the laser box. Can you plug it in? It's safe, don't worry, I've tested it. Okay, can you turn on the laser please, here from here? All right, so now on the screen, can you focus on the screen, on that red spot? Can you, all right, dimmer please. All right, can you move a little bit closer? Okay, so now what I'm going to do is, can you hold this for me please? I'm going to move this slit into the path of the laser. Does anyone have a visiting card? Card. Visiting card. Fine. Okay. So just wanna. What I'm going to do now is refocusing on the. Please turn off the lights a little bit more. I can begin to see the fringes. Is it possible to turn off the lights a bit more? Can it be fully dark at least in this region? Zoom in on this, zoom in, just get closer and zoom in if possible. The lights, that's all you can get for the darkness? Focus here. Unique spot. So if you want to come, it's more visible on the. So what you could see, do we have a laser pointer? My friend, do we have a laser pointer? That. Right. So what we can see here are fringes. So if I there is a central spot, a central maximum where there is maximum intensity, and if you look closely, and if you look really closely, there's a central spot followed by a dark fringe, bright fringe, dark fringe. So these are the interference patterns that the previous speaker was talking about. So this is a single slit diffraction image, and so it's really beautifully observable by naked eye in front of the screen. If you want to come here and have a look, that's fine. It's not as clear on the camera, but if you look at the screen, at the central spot, just to the left of it, there is a region of darkness, followed by bright, dark, bright, dark. Okay, and if I change the slit width a little bit, here I get these undulations in the intensity. Sorry, it's a bit hard to see. I should have a lens that could diverge this a little bit, but this is an interference pattern which demonstrates that light truly is a wave. And if I change the opening of the slit, the pattern changes. Here I'm blocking the light, I'm reopening the slit, I get the interference fringes again. On both sides of the central maximum, there are bright and dark regions. So it's really obvious from the naked eye. Let me try to move the screen a little bit closer. Here, can you see these? Now I think this is the best I can get. Bright and dark, bright and dark. Just to look to the right of those, of the central maximum. Okay? So this is how interference works. So thank you, Joseph. You didn't have to do much, but your company was really precious to me. Gave me a lot of solace. Thank you. Now I'm going to take away this slit. I'm going to kind of turn off the laser, and probably I'm going to turn on, I take off the slit. Okay. It's good to keep working in the dark. Okay. I need to see what I'm collecting. Okay, now what I'm going to do is, I'm going to turn on another light source, which you're very familiar with, and that's an LED. Now, can anyone tell me what a laser is? How is a laser different from another light source? What's so special about a laser? Just speak up. I can't see you, you don't have to be shy. Yes, please. What does that mean?
That means it.
What does monochromatic mean?
That means like it has one straight path.
Straight path?
Yes.
So that's not monochromatic.
Say yes. It has one single wavelength and the color is one.
A laser has certain properties. First of all, laser is generally light traveling in a straight line. Okay, that was your first point. Monochromatic means generally it has a range of wavelengths close to a single wavelength. A laser cannot have, any device cannot have a single wavelength because that's not allowed by the uncertainty principle, but it has a tiny range, a really tiny range about a central wavelength. Okay? Any other property of laser light? Generally it's strong because all the photons are marching together in the same direction. Any other property? This is a property which not many people are very familiar with, especially those that deal with lasers in a casual way, and that is coherence. A laser produces coherent light, which means that it's a very nice periodic pulse whose phase does not erratically change. And that coherence has a long, it extends over a long distance. Okay, so that's a property of lasers, unlike an LED. So now what I have in front of me is an LED, light emitting diode. Another marvelous invention of quantum physics, by the way. Now, how does an LED differ from a laser? So if I were to kind of demarcate the differences, how does an LED differ from a laser? Any takers to this question? Well, the good thing is that you don't have to be shy, and it's dark anyway. No one's going to see you. So, students, how does an LED differ from a laser? Any, yes, did I see your hand somewhere? The LED really is distinct from a laser because, first of all, the light from an LED, if it's not collected, it spreads out, it's not coherent, and it's not monochromatic. So it comprises a range of wavelengths. Okay? And how do we know that it comprises a range of wavelengths? So what we could do is we could shine this light onto an object that separates out the colors, separates out the wavelengths. Okay? So now what I have in front of me is, I turn on a laser, an LED. I need 2 hands for this. And now what you can observe is that when this LED shines light and falls onto an element which looks like that crystal-like object in the middle, the colors spread out. Okay? So what this object, which is called a grating, has achieved is that it acts like a color separator. It sorts out the wavelengths, and different wavelengths go in different directions. So this LED, which actually shows, this is a proof. The proof is in eating the pudding. The proof is the experiment itself. This experiment really shows that the light from an LED is coming out in different wavelengths, different colors, and if it is made to impinge on this grating, this color sorter in a way, the colors spread out, and you get a rainbow of colors. This is exactly how a rainbow is formed. So this source of light, LED, is like a color It is a combination, a mixture of colors, not a superposition of colors, but a mixture of colors, and those colors can be spread out. Like you separate out sugar from water in a sugary solution, you're separating out, unmixing the colors by putting different colors go in different directions. And by the way, we would like to do a quantitative measure of this. Okay, so any questions about this? We have a laser. Monochromatic light comes from quantum sources, but the light is not quantum. We have an LED, which gives classical light comprising of different colors. Okay, any questions about this? So by the way, this experiment that I've shown you is reminiscent of Newton's experiment from the 17th century, 1680s probably, when he actually did this dispersion experiment in his small dungeon laboratory in the University of Cambridge. Yes, please, there's a question probably.
So I want to ask whether we can use LED with a different color, maybe like red, green. Will it also bring the same results as this one? Or unless the white color?
If you were to use a red LED, then you would only get the red pattern. You would not get the green or the blue, because the red intrinsically is devoid of the green and the blue color. Okay, so this is a rainbow that we've made for you. Now what we would like to do is we would like to do this experiment in a more quantitative fashion. Okay, so I would like to show you the same experiment from the perspective of a spectrometer. How does a spectrometer kind of see this? So this is visual, and this is great for a demonstration, but if you want to become a scientist, let alone a quantum scientist, you would like to do quantitative measurements. So I would just like to show you a quantitative version of this. So I'm going to remove the grating. I turn off the LED. I remove the grating. I carefully put it back into my box. I now remove the screen altogether. I'm going to have to work in the dark a little bit. So here is an object that is called a spectrometer. The spectrometer is a quantitative device which can replace the eye. I mean, it can resolve the different colors, okay, in a quantitative fashion and provide you with a spectrum. A spectrum is a plot of intensity as a function of wavelength or color or frequency. So this is going to do a quantitative version of what we've seen, what we've just seen, okay? By the way, even though an LED is different from a laser, if a laser does not get enough current or enough energy, it will act like an LED. Okay, so just keep that thing in mind. Physics is beautiful, really. Science is beautiful. All right, so I'm going to have the spectrometer, and I have So now I have this piece of wire. This looks like a piece of wire, but it's actually a piece of quartz. It's a long fiber of quartz, and it's called an optical fiber. This is an optical fiber. So I'm going to put the light from the LED into this optical fiber and connect the output from this fiber into the spectrometer. Okay? So I'm going to see a visual pattern of the spectrum. Okay? fiber, connect it to the spectrometer. One end of the fiber points in the direction of the LED and the other end names to the spectrometer. And now I would like my cameraman friend to focus on my computer. So, here is my computer. So I'm going to switch on my computer without glasses, without wearing my glasses. It's a bit hard. And I open up a software which reads out the data from the spectrometer. But I've forgotten to connect the spectrometer with my computer, which I'm going to do that right now. Can you focus it, please? All right, so can you stay put? Can you just stay put, stay here? Yes, stay close to me. All right, so now what you can see on the, can you focus here please, on the spectrum? Oh, you can't see anything. So I never knew. Can you zoom out or? Okay. Let's try to see if I can change the color for this. Okay. I don't want to take any risks. So right in front of you, you can see a spectrum. So on the x-axis of this graph is wavelength. Wavelength corresponds to color. And on the vertical axis, we have the amount of light or the intensity of light for that color. So this is a spectrum. And so what the normal eye cannot observe, a measuring instrument tells you. So the measuring instrument here, which is our spectrometer, is revealing that this LED has a bimodal distribution of wavelengths. One mode around 420-30 nanometers, which corresponds to bluish, blue-violet, and one mode between 500 to 700, which corresponds to green and red. So this composition, this mixture of wavelengths is giving you the impression of white light. So what I could now do is, I could pick up an element hello. I have an element in my hand, and what I'm going to do is I'm going to put that element in between the LED and the spectrometer. And this is what is called a filter. This filter is going to allow a certain wavelength of light to go through. So as I put my LED, as I put the filter in between, I just get a narrow peak. Okay? So I've made monochromatic light. I've filtered out all other wavelengths and just kept a wavelength of light close to 500 nanometers come in between. So I've separated out, I've blocked all wavelengths and just allowed one wavelength of light to pass. And the light that now reaches the spectrometer is still not coherent. It's monochromatic, but it's not a laser. It's still incoherent light, light from a white light source. Now, how does a laser produce light? A laser produces light by a complicated process of electronic transitions between three levels. One of those levels is a metastable state in which the electrons live longer. So it's a complicated dynamics of electrons moving around levels. An LED produces light by the transfer of electrons and holes across a p-n junction, and when they recombine, the electron and the hole recombine, they produce light. So they produce light by different sources. But let me show you another mechanism for producing light. So I turn off this LED. Okay. So far so good with the LED. The spectrometer has come back to its datum level. Now I'm going to show you another source of light. In the previous lecture, you were introduced to the idea of a gaseous vapor in a vacuum cell. What was that gas? Rubidium. So there were rubidium atoms trapped in a vacuum cell, which were your quantum sensors. Now I also have a gas. And that gas is, at the moment, the gas that I have is mercury. Now I have mercury inside a glass tube, a sealed glass tube. You've already seen the concept of wavelengths. LED has a broad spectrum of light. Laser has just one kind of peak, even though I didn't show it on the spectrometer. But now let's see how the emission, how the light from a gas looks like. So what is your prediction? If I were to shine the light emitted by a gas, a vapor of mercury atoms that have been excited to some higher energy levels by an electric voltage, how would the spectrum look like? Any guesses? Will it be a hump, a nice, smooth, camel-shaped hump? Will it be a single peak? What is your expectation? Any predictions? As scientists, you would like to make predictions. Any predictions, my friends? Okay, let's see. Of course, it's not intuitively obvious, so we need to focus on this again. Let me turn on the mercury lamp. So the mercury lamp is here in front of me. It's a sealed tube which has mercury vapor inside it, and I give it a strong electrical voltage, a high electrical voltage, about 1,000 to 2,000 volts, for which I brought a power supply. So I switch on this lamp. First of all, forget about our dear friend the cameraman. Try to see on the screen. Can you, for a minute, my friend, focus here? I want them to see this color. Okay, so this is our tube. In the middle, please. Just in the middle, here. Yeah, that's it, perfect. So this is our tube. It's evacuated with a tinge of mercury vapor, a slight bit of mercury vapor. Mercury is a complex atom, as you know. And I turn on this supply. First of all, observe the color. Okay? So it has a distinctive bluish silvery color, and the color appears more iridescent, more beautiful in actuality, in fact, than it does on the screen. Okay? Now, if I were to look at the spectrum, now if you were to focus here on the spectrum, you see a jungle of peaks, a forest of peaks. See how beautiful this is? Now this is a cornucopia, a jungle of peaks. Narrow peaks, but not one, a multitude of peaks. All of these colors are being emitted by mercury vapor, by the mercury vapor. And these occur at precise wavelengths. Okay? Let me turn off this supply because I don't want this to overheat. So this spectrum is made up of a multitude of peaks. And each of those peaks correspond to a transition from one level of an atom to another. Suppose I'm standing here. I jump from this level to the bottom level. My energy drops. And I emit a certain wavelength. Suppose I take a jump upward and then come down. The energy gap changes because I have a different trajectory of energies, and the energy lost is different. So I get different energies. Different energies of photons correspond to different frequencies. Now let me, for your curiosity, let me change the gas. Let me switch to another gas. This time, neon. So I'm going to take out this tube. Slightly complicated process, requires a bit of force. I don't want to, okay. I've taken out this tube, and let me put in another. So this is a tube that comprises neon. So there's a question about chemistry. Does anyone know the atomic number of neon? Sorry? 10. Mercury? 10? Mercury has to be different. 18? No, mercury I think is 23 or 26 or something of that kind. So mercury has a large number of energy levels. And that's why large number of transitions are possible. So you get this large cornucopia of peaks. Now let's test this out with neon. So now this is trapped neon vapor in a sealed vacuum tube. So I load this tube. So I loaded the tube, and now I'm going to impose a large electric voltage onto this. Can anyone predict the color that's going to emanate from this tube? What color would it produce? This is something you should know from your daily lives. Neon. What color does a neon sign give? Speak up. Speak up, please. Multiple colors. Sorry, pink? Yellow. Let's see. I think the digital generation doesn't know about neon signs. So this is a distinctive red color. Okay? This is neon. This is neon glowing, a source of light, another source of light, hot atomic vapor producing colors. And could you focus on the screen, please? Now here is the spectrum of neon. Now neon is giving a far less number of peaks because the atomic number is smaller. 10 is the atomic number, so probably 2, 8, and it's a inert gas, you know. It's in the second period of the periodic table. Not many energy levels are possible. So it's excited, but to higher levels, and whenever de-excitation takes place, a photon is emitted of a particular wavelength. But this is not quantum light, but it shows the quantization of states, quantization of energies inside an atom. All right, so for the last part, oops. So I'm going to shut this down. I would like the lights to be turned on, please. All right, so now we have to focus to a different thing. So we're done with this. Okay. So any questions? I just take probably 10 more minutes. Is that okay? And I would like to have 5 students come here, please. 5 volunteer students, gender bias, no gender bias, half boys, half girls, or 6 students, kind of, please come to the podium while I gather my stuff. Okay, 5. With some girls. Are the girls too shy? Are you coming? All right. So one more, please. And you can sit at the front. We'll give you the privilege of sitting here. Sit at the front. All right. So now I'm going to do something interesting. I want you, all 5 of you, to make your own light source of a different color. Let's see how we can do that. Okay, so which school are you? Are you a student? You're doing what?
Service.
Service. What is service?
I'm at Parliament of Ghana.
Oh, okay. And your school students? Which class?
Grade 11.
11. Your name?
Princess. Princess.
Princess?
Yep, what? Yes, please.
Grade 12.
Speak up, please. Give a mic.
Grade,
Speak up.
grade 12.
Grade 12, your name?
Priscilla.
Okay.
Peter, grade 12.
Grade 12? Your name again? I didn't.
Peter,
Peter?
Henry, grade 11.
Grade 11. All right. You're from the same school? 2 different schools? Okay. And you went to a different school? All right. So I want them to make their own light sources with molecules, with ions. Okay? So this is going to be something interesting. And I hope there are no fire detectors, fire alarms here. Let's see. Okay? So here's a beaker for you. So we need 5, 3, 4, 5. And can I get some water in this, please? As a safety mechanism. I might need to extinguish something. All right. So now I have. So remember our goal. We're trying to make our own light sources, different colors. This is water. So keep that in mind. We don't want to mix this with the other thing. So whenever we want to do experiments, we have to be safe. And you always want to do experiments of this kind under supervision. Slightly more experienced than you. Now this is a liquid, a molecule. It's called ethanol. All right? So can you hold the mic for me? So I'm going to pour a little bit of ethanol in each one of these beakers. Little bit. Okay? Here you go. Here you go. Beacon number 3. Beacon number 4. Beacon number 5. So any properties, does anyone remember the formula for ethanol? Yes, speak up.
COOH.
That's acetic acid. That's ethanoic acid. Ethanol.
CH3H2OH.
CH2OH, all right? Methyl group, methylene group, hydroxyl group. That's ethanol. So it's an alcohol, okay? It's a hydrocarbon. And any properties that you remember for ethanol? Does it catch fire? Does it easily catch fire? Yes. We're dealing with a flammable liquid here, so we have to be careful. So this is ethanol, and I'm really grateful to you for arranging this for me and to Sarah. So I couldn't bring this in my suitcase from Pakistan. Otherwise, they would have deported me or something. All right, so this is ethanol. Don't drink. It's alcohol, but don't drink. It's faded. All right, so now I would like, now is there any school teacher here who does chemistry or physics? Any school teacher here? Because after this lecture is over, I'm going to donate this stuff to them. The school teacher? All right. Now I'm going to give you some salts. Sodium chloride. Okay, just hold it for me for a minute. Calcium chloride. Copper chloride. This goes at the end. Lithium chloride. And finally, a really interesting one. All of these are chlorides. Okay? What's your salt? What's your cation? What's your positive ion in this salt? Sodium. Yours?
Calcium.
Calcium.
Copper.
Copper.
Lithium.
Lithium.
Go. Boric acid.
Right, so he doesn't get a salt. He gets an acid. Wow. But it's a benign acid, boric acid. Do you know where boric acid is used? It's a disinfectant used for washing, especially the eyes. Okay? Now what I would like you to do is, let me do this for one of the students, so, and the others would repeat on their own. So I'm going to take a little bit of the salt, this acid in this case, and kind of pour this into the ethanol. Okay? Just a little bit, just imagine how much I'm putting it. Now, can you do this for your own respective beakers without tumbling them over? Here you go. Here's yours. And remember your salt. Done? Everyone? Okay. So now I'm going to give you a utensil to kind of stir this. Stir it well, but not too well, so that there is some undissolved solid. So I brought these stirrers. I think my wife has wrapped them really well. Can you stir, please? Nice. Just half a minute more. Okay, don't tumble them over. I just need this. Oh, this should be fine. Can you hold this? Okay, that's fine. And now I brought some candy for you. It's candy floss. Okay? Here's your candy. Yours. Number 3. Number 4. Number 5. Don't start licking on it, it's not candy by the way. Alright, so
Taking this with us, right?
alright. I'll receive your stirrer. Thank you. And you can put your salts here so that you can comfortably handle this. Now, could you kind of, oh, I have a matchbox with me. So what I'm going to do now, I'm going to ask these students to kind of impregnate this solution or mixture onto this cotton ball, and I'm going to put fire on it. Okay, and I'm going to see what colors do we get. Okay, we have to do it quickly so that the ethanol does not vaporize. So let me do this for one student, and then the others can repeat, and while I put on fire, and you hold it like this. Okay, it's safe. It's safe. Okay, doors open. Can you open the doors, please? All right, so. Okay, hold it, please. Extend your arm.
Which are this?
This was boric acid, green color. All right? So where is this green color coming from? This is coming from the energy level structure of boron. And it's not permanently green because it's burning and there are other materials mixed in. Carbon has its own color, the soot is burning, but it's a distinctive green color. That's what the predominant color from boron ion comes out to be, because which actually shows that the energy levels inside the boron atom are quantized. All right, so if you're tired, can you just move this away, please? If you're tired, you can just perch this in here, or you want to hold it. You fine? All right. So can you move to that side? Can you try? What was your salt? Lithium. I want you to go at the end. What was your salt? Copper. Let's check what distinctive color copper gives. Now this is a light source which the students have generated themselves. They need a round of applause. Copper, greenish, again. With a distinctive blue tone. You can see those flakes of blue coming in? That's copper. Blue-green. What's your thought? If you're tired, be tired. So calcium, okay. Let's see. Extend your arm up. Don't be shy, don't be afraid, it's not going to hurt you. This is calcium. And what's yours? What color does sodium give? Yellow? Extend your arm. You really want to turn off the lights to see these colors? We'll do that in a minute. Be careful, be careful. Let's move on to lithium. And then I will request to turn off the lights and watch your head. Please. I love lithium and boron. Turn off the lights, please. Can someone turn off the lights, please? Complete darkness would be very nice. Now can you see the colors a bit more clearly? Right? So you speak up your ion.
What?
Your ion, your atom.
Is boric acid.
What's your atom in it which is giving the color?
Boron.
Boron, yes.
Copper.
Copper.
Calcium.
Calcium.
Lithium.
Lithium. Just atomic number 3. Look at this beautiful resplendent color.
Sodium.
Sodium. So this is how you create colors. This is how pyrotechnics work. And this is quantum. The quantized energy levels inside these atoms, since the atoms have now been excited to higher levels because of the temperature, and when they de-excite, they are giving these distinctive, beautiful colors. What else a proof one would need for the quantization of energy level? So in order to extinguish this, where was our water? There. I think this will produce some smoke. So what you could do, we'll close this session. What you could do is you could walk out of the building and not go to the washroom because this will produce smoke. Just hold it, or you need to put it in I don't want to do this inside the room because this is going to produce smoke. So it's best to kind of let it extinguish on its own. Okay? Don't kind of blow on it. You just hold this. You want to walk a little bit outside. That's going to be okay. Your other friends could see. So thank you very much. If you have any questions, I'll be happy to answer.